In this video, I will be going over some common homework questions that students have had in the past on the Finding Limits Algebraically worksheet. Listed here are the problem numbers that I will be going over. Feel free to move the video forward or backward to find a specific question you have if you don't have a question on all of these. Alright, so starting off with number 11, we want to find the limit as t approaches -2. First off, just trying to plug it in doesn't work because we end up getting 0 over 0, and so we want to factor. So the numerator, the t cubed plus 8, is in the form of a sum of cubes. We could rewrite it as t cubed plus 2 cubed. And remember the factored form of a sum of cubes, something like a cubed plus b cubed, is a plus b, a squared minus ab plus b squared. So we could factor the numerator into t plus 2 times t squared minus 2t plus 2 squared, which would be 4. Sorry. Alright, all of that is divided by t plus 2. We'll go ahead and cancel that as a common factor, and then we can plug in the value of -2 into what's left in the numerator. So we end up with 4 plus 4 plus 4, giving us a limit value of 12. Okay, the next one, number 14. So this one is also tricky. If we were to plug in 1 in the numerator, we have 1 plus 1 minus 5 plus 3, so that'll be 0. 1 in the denominator becomes 1 minus 3 plus 2, which is also 0, 0. So we need to attempt to factor. However, just by looking at this, there's no factoring technique that would work, and so we want to think about doing synthetic division. So on both the top and bottom, because the x value of 1 made the polynomial equal to 0, that means that both the numerator and denominator can be divided by the factor x minus 1, and that will help us to get a factored form. So let's look at doing our numerator first. We can do synthetic division, so we'll turn it into a positive 1. We have 1, 1, negative 5, 3. And we should get a remainder of 0 because we know that x minus 1 is a perfect factor. Now, this is an x squared term, or an x squared polynomial, so we have x squared plus 2x minus 3. If we were to plug 1 in here, it's still equal to 0. 1 plus 1 minus 3. So we actually want to keep going. So because we tested it again, 1 makes that 0 again, we can divide that by x minus 1 again. Sorry, 2 plus 1 is 3. Okay, we get a remainder of 0, and now we have x plus 3. So finally, this is going to be good for the numerator. 1 plus 3 will give us 4. Okay, so it's not 0. So let's go ahead and write that as our numerator. Now we're going to do the same thing with our denominators. We'll divide it by x minus 1. Notice how we're missing the x squared term, so we're going to put a 0 in its place. Remainder of 0. 1x squared plus x minus 2. If we were to plug in 1 here, again it would be 1 plus 1 minus 2, which gives us a 0 on the denominator, which we don't want. So we're going to divide it by the x minus 1 again, because 1 made that equal to 0. Alright, and this gives us, again, something a little better, x plus 2. Now finally we can plug in our x value of 1. So we have 1 plus 3 over 1 plus 2, giving us a final limit answer of 4/3. Okay, looking at number 16, limit as x approaches 5. If we plug 5 in for x, we get 5 over 0, which is no good, so we're going to attempt to factor and cancel. However, when we factor, we see there's nothing that can be that can be canceled. So that means that our answer will either be positive infinity, negative infinity, or does not exist. We need to figure out the limit coming from the right-hand side and the limit coming from the left-hand side. So we're going to make a chart. The limit coming from the left, we could think about plugging in the x value of 4.99. So this is going to end up being positive over. Now this is going to be a positive, and that's going to be a negative. So a positive times a negative is a negative, and positive divided by negative is negative. So the limit coming from the left side is going to be negative infinity. Now we want to check the limit coming from the right-hand side. So we could plug in something on the right side, something like 5.01. So our numerator is positive, and our denominator will also be positive. So that tells us the limit coming from the right is positive infinity. So because these are different, overall, we can say that our limit does not exist. Number 20, if we were to plug in the value of 5, we have 5 minus 5 giving us 0 on the denominator. The absolute value of 0 is still 0. There's no way that we can factor or cancel here, so it's got to be equal to positive infinity, negative infinity, or does not exist. So let's do kind of actually very similar to number 16 that we just talked about. The limit as x approaches 5 from the left side, we can plug in 4.99. Now 4.99 take away 5 will be negative, but because it's inside of this absolute value, that's going to make it positive. So we have a positive over a positive. If we look at what's happening as we approach 5 from the right side, it's also going to end up being positive. Sorry, those are absolute value bars. Looks like a 51. It's not. It's also going to end up being positive over positive. So because it's the same, that limit is equal to positive infinity. All right, number 21, if we plug in 3 into our denominator, it's going to make our denominator 0. There's no way to factor or cancel, so we'll need to make a sign chart for this one as well. We could think about plugging in to the left 2.99, and to the right of 3 would be 3.01. Now when we're plugging numbers in, it actually, I think, is easier to do if it's in factored form. So I'm going to go ahead and factor that denominator. So let's think about what would happen for the x value of 2.99. 2.99 squared is positive, but put that negative in front, that's going to make it negative. That's going to be a negative on the top. On the bottom, 2.99 take away 3 will be negative. But it happens twice. A negative times a negative is a positive. So negative over a positive, altogether that's positive. I'm going to switch colors for the other one. For 3.01, same thing. If you square it, it's positive. But then that negative in front is going to make it negative. On the denominator, 3.01 take away 3, that's going to be positive. Positive times a positive is a positive. Negative divided by a positive is a negative. You know what? This needs to be a negative. Sorry, negative divided by positive is negative. Okay, so because they're both approaching the same sign, the same direction, this limit is going to be equal to negative infinity. Right, so then if they're different, that's when it does not exist. So there's kind of an example of each situation there. Okay, moving on, now we're looking at some piecewise functions. So we want to think about just plugging it in. This time we're dealing with the x value of 3 as x approaches 3. So for the top part, 3 minus 1, we get 2. When we plug it into the bottom one, 2 times 3 is 6, minus 3 is 3. So because these are different, they're not the same, we're going to say that it does not exist. Let's try this one. The limit as x approaches negative 1. So if we were to plug in negative 1 to the top, that's negative 2. If we plug negative 1 into the bottom, it's also negative 2. So because they're the same, we'll say overall our limit is just equal to, see if I can extend this, there we go. The limit is just equal to negative 2. Okay, the next one, 24. So we have another piecewise function. However, we cannot plug it in because if x is 1, it makes both denominators 0. There's no way to factor or cancel to make it not 0. So we're going to need to do a sign chart. This is telling us that our limit will be equal to positive infinity, negative infinity, or does not exist. So something to the left of 1 could be 0.99. Because it's less than 1, we have to plug that into this bottom function. So think about doing 0.99 over 0.99 minus 1. This is going to be a positive over a negative, which is negative. Now, on the other side of 1, we could plug in 1.01. Because that's greater than 1, we're going to need to plug it into the top function. So that's going to end up being a negative over a positive. And a negative divided by a positive is a negative. All right, so because they're the same sign, they're going the same direction, so we can say that our limit then will be approaching negative infinity. Okay, and then moving into the final section here, 28 through 36, all of these limits are either approaching positive infinity or negative infinity. So remember before, in one of the first examples that we did, if we're ever doing the limit of a constant value, this is the horizontal line, y equals x, the y value will always, y equals 6, the y value will always be 6, so the limit is just 6. For this one, the limit as x approaches infinity. So we don't see a denominator. We could think of the denominator really being 1, and the degree of the denominator would actually be 0. So if you don't see an x variable, it's the same as x to the power of 0. So the degree on the top is greater than the degree on the bottom. And so it's a top-heavy situation. So we're interested in the limit as x approaches infinity, positive infinity. So we want to think about plugging in a very large number. If we plug in a very large number here and then it multiplies by negative 2, it's going to become a very large negative number. And if you add 11, it's not going to make a difference. It's still going to be negative. So that will just equal negative infinity. Similar situation for number 30. This one is also top heavy. As x approaches negative infinity, we want to think about plugging in a really, really small number. And really, when there's multiple terms going on here, we really just need to think about what's happening with the first one, the one with the highest exponent, because that's either going to be so large or so small that everything behind it is not going to make a very big difference. So if we plug in a really small number like negative 1 million, if that's raised to an even exponent, it's going to be positive, and it's going to be very large. Multiplied by 3, it's still a very positive large number. Everything happening behind it, this is going to keep it positive. Actually, it's all going to be positive. A negative to an odd exponent is negative. Multiply that by negative 3. So these first 3 are going to result in very positive large numbers. And so we can assume that it's going to equal positive infinity, a very large positive number. Okay, and then finally, number 35 and 36. So these are two more top-heavy situations. So in 35, as x approaches infinity, we think about plugging in a very positive large number. The numerator will be positive, the denominator will be positive, so that will go to positive infinity. On number 36, the leading term, it's not in the correct order, so the negative 5x to the third, we could actually rewrite that so that it's in front. Just going to rewrite the denominator. Okay, limit as x approaches negative infinity. So we want to think about plugging in a really, really small number. We really just want to focus on what's happening with the first term on the top, with the highest exponent, and the first term on the bottom. So if it's a really large negative number to an odd exponent, it's going to be negative. Multiply that by -5, it's going to become positive. So you have a really large positive number here, and whatever's behind it is going to not make a very big difference, so we can assume that the numerator is going to stay positive. And then thinking about our denominator, a really large negative number squared will become positive. Multiplied by +9, it'll stay positive. So we can say that this one will also be approaching positive infinity.